All right, so now that we understand EIP2537 on a high level, in the second part, we'll be looking at the code changes in the EVM that come along with it. So at the end of this video, you'll have a really good understanding of how precompiles work within the EVM, but also how you could very easily add a new one, for example. All right, so as I have done in previous videos, I like to use the REVM codebase for this, which is a Rust implementation of the EVM, because not only is it fast and so on, but it's also highly flexible and can easily be used to experiment with new features of the EVM because it's so easily customizable and therefore makes a lot of sense to learn for anyone. So a good way to understand how precompiles are added to the EVM is to look at a specific PR that implements an EIP which introduces new precompiles. And therefore EIP2537 is good fit because, as we have discussed in part 1 of this video series, it adds some precompiles to support math on the BLS12-381 elliptic curve. And the PR that implements this is this one, I believe. Yeah, that looks correct. This is the PR that implements EIP2537 and adds it to REVM. But instead of going through all these file changes, I'll walk you through it within the context of the full code base, since I already studied it. All right, so the best place to get started is probably here, which is the ETH handler trait, which is kind of defining the interface to REVM's execution logic. And since precompiles called within the execution logic of the EVM, we'll probably get smart about those in here. And as I already mentioned, REVM is not only an EVM, but an EVM framework. And hence it has all these associated types that define various aspects of the EVM and that anyone can implement themselves. We can see here, for example, that precompiles is one of those associated types and is only bound to implement the precompile provider. This is really cool if you think about it, because it allows any EIP author to experiment with a new precompile, for example, and quickly have EVM prototype with that new precompile included. All right, so let's have a look at this precompile provider trait that has to be implemented by this associated type precompiles. And if we click on it, we see that it has this run method, which probably is the one that executes the precompile by taking in the address at which it's located. And then we can also see it has this contains method, which returns a Boolean and takes in an address, again, probably the address of the precompile. And this basically checks if the address provided is precompile address or not. Now, if we think about it, the fact that these two methods are being exposed kind of makes sense for the precompile provider, because I don't know how familiar you are with Solidity, but if you are, then you probably know this EC recover method, which under the hood gets compiled down to call to the 0x01 address where the EC recover precompile is located at. And for context, when the EVM executes a smart contract bytecode, it creates a new frame for each call opcode to another address that it encounters. And thereby it builds up this so-called frame stack. So now, without needing to actually look at the frame creation logic of the EVM as it's implemented in REVM, we can probably assume that when the bytecode is executed and whenever it encounters a call opcode, it makes use of this contains method we just saw to check if the address is a precompile or not. If it is, then it loads the natively built-in precompile method. And if it's not, then it just loads the smart contract bytecode at that address and executes it the normal way through the interpreter opcode by opcode. All right, so as I have already mentioned, the REVM is an EVM framework and it ships with the Ethereum mainnet EVM by default. So if we want to look at how the Ethereum mainnet EVM is implemented, how it implements this trait, we have to look at the implementation, which we can find normally in the precompile provider should be, because this is just the interface. So we need to go at the actual implementation, which can be found here. So yeah, we can see that there's this ETH compile provider struct, which has a precompiled field. And this trait that we looked at, the precompile provider, gets implemented here for this ETH precompile provider. And it has this one method. Here's the implementation. So as we've seen, it takes in the address of the precompile. It takes in some inputs as bytes. Then first it checks if the address is even a true precompile. If it's not, then it just returns a result with none. Then next, it initializes this interpreter result. But importantly, here is where the actual precompile is being called. So as we'll see later, the precompiles are actually function pointers, and here this function pointer gets dereferenced with the inputs that were passed to this run method here. And then it modifies the result according to the execution of that precompile. And this is if the precompile method gets executed successfully. In the lower part here, it handles some errors. But now let's have a look at what these precompiles actually are. Because this is where we'll not only find how EIP 2537 and all its new precompiles are being implemented, but we'll see how all of the precompiles in the Ethereum mainnet are implemented. Now, if you look at the constructor method of ETH_compile provider, you can see that it takes a spec ID, which defines the fork and hence the precompiles with which this EVM is configured. And so we can see here that the precompiles field from the ETH precompile provider gets assigned this value here, which is a call to the constructor method of the precompiles type. So let's have a look at what that is. So we can see here that the precompiles type is a struct with two fields, an inner field, which is a hash map of every precompile address, with an associated value, which is a function pointer to the implementation of the actual logic of the precompile. And then here we also have a set with all precompile addresses. Now, in the implementation block, we can find the constructor method, which takes in the spec ID. And given the spec ID, we call a function named after the specific Ethereum hard fork for which this spec ID stands. And if we look at each of these methods, it's actually quite nice to see because it lets us nicely track the evolution of Ethereum precompiles over different hard forks. So each fork here introduces a new precompile or modifies existing ones. So Homestead is the first fork that REVM, this specific implementation of the EVM, supports. And we can see here that it only had 4 different precompiles. So it had ETH_recover, SHA-256, these other ones, which I don't even know. And then next we can see that Byzantium fork took everything from Homestead, but extended it with some curve operation on this BN128 elliptic curve, and also some modular exponentiation precompile. But so we are interested into EIP 2537, and that is shipped with Prague. So let's have a look at Prague. All right, so here it is. And this part is probably what, if we think back to the PR that we actually wanted to look at, this block is what has been added by this pull request to support EIP 2537. And so this will return a box of all the precompiles that are shipped with Prague. So what are those precompiles? First, we can see that we take all precompiles as they existed under Cancun, the latest fork that changed anything regarding precompiles. And then we have these new precompiles that are being added. And this contains all these new curve operations on curve BLS12-381, as we have seen under the spec of EIP 2537. So these new precompiles have their own module. So let's have a look what precompiles return from that module. So precompiles, as we could have expected, returns an iterator of all the new precompiles that allow to do various operations on this BLS12-381 curve. So let's look just at the first one. We are not interested to go into the actual cryptography and look at the individual implementations. We just want to get a sense of how precompiles are implemented. There's this G1 add precompile, which I don't know if you can recall from part 1 where we went through EIP 2537 on a higher level. But we talked about this add operation on that curve. And yeah, this is where it's being implemented. And so it has its own module, and we take the precompile from it. So that precompile constant is of type precompile with address, and precompile with address is a struct with 2 fields, one of type address and one of type precompile function, and precompile function is just a pointer that returns a precompile result. In any case, let's look at what we assign to this precompile constant for the G1 add precompile. So the precompile with address takes in an address, and that address is obviously where that specific precompile will be located at. As defined in the specs, if we look back at the specs here, we can see that the G1 add operation lives at address 0x0b. And that is exactly what is defined here. And then as the actual implementation of the precompile, we have this function pointer to this implementation body, where it's out of scope to actually go through the implementation. First of all, because I'm not the best suited to talk about this. But yeah, if you want to link any kind of details or good content about the actual cryptography involved here and how it works, that would be really cool. In any case, this kind of wraps it up here. I hope this helps to get a good sense of how precompiles fit in within the EVM. And yeah, it gives you an idea about this new EIP 2537. Again, like always, please add any comments and correct me about anything I said. All I'm doing here is really learning in public. Also, if you want to discuss any of this further, feel free to join my Discord. You can find the invite to my Discord channel in my YouTube description. In any case, thanks for watching and see you next time.